Hi, welcome to an academy. Welcome to an academy. An academy is the India's largest online learning platform. Now we are happy to announce that now we are going to providing the classes to GATE and engineering service students. About myself, I G Venkatrao. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am pursuing PhD from JNTU Kakinada, and my specialization in PhD is VLSI design. Now, first we check how to get the Unacademy Learning app. If this app is in your device, it's fine. Otherwise, just install it. Now, we check the procedure how to install it. Just go to Play Store in your device. Just type an academy in that. Once you type an academy in that, now you get an academy learning app like this. An academy learning app like this. Okay. Once you get the Unacademy learning app like this, at this end there is a install button. Just click on that install button. It will install the Unacademy learning app into your device. Now once you open the device, once you open that app in your device, it will shows what are the different courses available in Unacademy and who are the top educators handling the subjects in that courses. If you observe few of the top educators from Unacademy, Tiwari sir, he is a IIT topper. Ankit Goyal sir, he is obtained All India rank twice, All India topper twice in electrical engineering. And Jain sir is the top experienced faculty from computer science. And Jaspal Singh sir, he is the ex-IAS officer. His rank is All India rank 4. Here are the top faculty. Now, here are few more top educators working in Unacademy. Now, we are happy to announce that recently we started 2 new batches for GATE 2022 and GATE 2023 in different disciplines. Now, just we glance those. Now, there is a Ascend batch for GATE 2023 in mechanical engineering. This batch started from 8th February 2021. Here are the top faculty who are handling the subjects in that. Next, there is a Evolve batch for GATE 2022 in mechanical engineering itself. Here are the top faculty who are handling the classes in that. This batch also started from 8th February 2021, and there is a Ascend batch for GATE 2023 in civil engineering discipline. Here are the top faculty who are handling the subjects in civil engineering, and this batch started from 8th February 2021. And there is a Evolve batch for GATE 2022 civil engineering itself. This batch started from 8th February 2021. Here you observed or not, we categorized clearly GATE 2022 batch as well as GATE 2023 batch. The intention here is to provide a proper information to the student based on their time. See, for GATE 2022 they have only 1 year time. For GATE 2023 they have 3 years of time. Once they have 3 years of time, we will conduct more number of examinations. Okay, there is a chance of repeating the more number of times. But for GATE 2022 we have to complete the syllabus early and we need to conduct more exams. Okay, so their plan is different, their plan is different because they have only 1 year and they have 2 years of time. So that is the intention, to divide both the separate batches. Okay. Next, there is a computer science and information technology for this Evolve batch for GATE 2022. This batch started from 8th February 2021. Now there is a Ascend batch for GATE 2023 in electrical engineering. This batch started from 1st February 2021. And again Ascend batch for GATE 2023. This time this is for electronics and communication engineering Here are the top faculty handling the subjects here. This batch started from 1st February 2021. Next, there is a eval batch for GATE 2022. This batch started from 1st February 2021. This is for electrical and electronics engineering. And the next one is eval batch for GATE 2022, electronics and communication engineering stream. Here are the top faculty who are taking the classes for electronics and communication engineering. Okay, now we are moving to chemical engineering. There is a eval batch for GATE 2022 chemical engineering. Okay, we are happy to announce that we are starting chemical engineering also. Sorry, because all of you know that outside it is not possible to get the chemical engineering training for GATE examination. So we gathered top faculty from chemical engineering. We started a batch, and this batch started from 25th of January. If any of your friends are in the chemical engineering department, please inform them about this. And don't forget to use my code VRAU10 during subscription. VRAU10 during subscription to get 10% discount. Okay. Now here you have two types. Now once again we glance what are the different courses, different disciplines available. Okay, here mechanical engineering, electrical engineering, civil, production and industrial, computer science and IT department, ECE, instrumentation engineering, okay, and chemical engineering. These are the different engineering disciplines available from an academy for the students who are appearing for their GATE and service examinations. And here we have two plans. First one is the plus subscription. The second one is iconic subscription. Plus subscription is the basic plan. Iconic subscription is the next level of the plan. In this next level, we are providing a personal coach to each and every individual student. Personal coach to each and every individual student. Okay, please note on this point. Personal coach we are providing. So there is a commonalities between this. India's best educators are going to take the classes for both, and there are live interactive classes for both, and structured courses and PDFs are provided to you, and live tests and quizzes we are going to be provided. Now the purpose of this personal coach here is whatever the test you've written, they are going to analyze this test. Okay, after analysis of the test, they are going to prepare a study planner. Okay, in that during the analysis of your test, they will note where you are strong, okay, where student need more preparation on which topics, and in where student doing mistakes. They will note down all these things in a proper way, and based on these gaps, they will provide the guidance to the student in the form of a proper study planner, and by suggesting the respective faculty to take the classes on that respective topic. Okay, by providing these additional things, they will fulfill the gaps in their preparation. So at the same time, they provide proper study material to them. Now by following these through properly, any student can success in the examinations. Okay, so that is the importance of the personal coach we are providing. Yeah, now just we check the price here for plus subscription. For plus plan, in plus plan we have 1 month plan, 3 months plan, 6 months plan, and 12 months plan. 18 and 24 months also is there. So as a faculty, my suggestion is join minimum 1 year plan. That is useful to you completely. Okay, so each and every course you can complete in detail, and you can practice more number of tests. How many number of tests you are going to be writing is the one of the important criteria before examination. Okay, so the cost for 12 months subscription is 30,250 rupees. After getting a discount of 10% by using my code VRAU10 during subscription, you get it by 27,225 rupees. you get it by 27,225 rupees. Okay, now I'm moving to next plan, Iconic plan. Okay, Iconic plan, it has two subscriptions, 12-month subscription and 24-month subscription. 12-month subscription cost is 50,250 rupees. After using my code VRAW10 during subscription, you get it by 45,225 rupees, 10% discount. Okay, for 2 years this is 74,000. By getting 10% discount, you get it by 66,600. Okay, so my dear students, please don't waste your time. Whatever thing is happened at outside, your learning process should continue, no break in that. Okay, so don't waste your time, join as early as possible and can get most benefits. Okay, now I'm thanking to one and all for joining our class. Now we are moving to our topic. Now today's topic is problems on PN junction diode. Already we completed different topics on PN junction diode so far. Now we are moving to problem session. Okay, now first see this problem. First problem, consider a silicon PN junction at room temperature having following parameters. Doping on n side 1 into 10 power 17 per centimeter cube. Doping on n side means it is Nd. Nd they given it as 10 power 17 per centimeter cube. Depletion width on n side depletion width x n naught is 0.1 micrometer. So we can write this is 0.1 into 10 power minus 4 centimeter. Finally it is 10 power minus 5 centimeter. Leave it. Depletion width on P side 1 micrometer, that means xp naught 1 micrometer, that means 10 power minus 4 centimeter. Now intrinsic carrier concentration Ni 1.4 into 10 power 10 per centimeter cube. Thermal voltage Vt 26 millivolts. Thermal voltage Vt is 26 millivolts. Vt 26 millivolts. And permittivity of free space 8.85 into 10 power minus 12 farad per meter, and dielectric constant is 12. Sir, and one more. Sir, before going to solving any problem, just I am going to calculating the epsilon value, because this epsilon is going to be we are using continuously in all problems. Okay, see, we know the value of epsilon. Epsilon is epsilon naught into epsilon r, we know that. Okay, epsilon naught value is 8.854 into 10 power minus 12 farad per meter into epsilon r. See, for silicon epsilon r value is 12. In some problems you get epsilon r value for silicon is 12 and exact value is 11.8. Not much variation, so I am taking that 11.8 standard value, and this is going to be 8.854 into 11.8. 8.854 into 11.8, that is a 104.47 into 10 power minus 14 farad per centimeter. I am changing this meters into centimeters, that's why it became 10 power minus 14. Now we can write this is 1.04 into 10 power minus 12 farad per centimeter, or 1.04 into 10 power minus 10 farad per meter, as you wish. Okay, you can use any one of this. So 1.04 and 1, not much variation. That's why now onwards I am going to taking epsilon value approximately 10 power, that means 1 into, so its intention is 1 into 10 power minus 12 farad per centimeter, or 1 into 10 power minus 10 farad per meter based on the requirement. So now onwards I am going to using, this is the epsilon value. Okay, no calculations, nothing, no need to waste time to calculate the epsilon value. Now I am moving to problem. Yeah, sorry. Now, so this is the data they given, and the built-in potential of the junction is, so we know the built-in potential. Built-in potential is V naught. Contact potential or built-in potential both are same. It is V naught equals to Vt into Ln of Na into Nd by Ni square. That is the equation for contact potential. Here we know the value of Nd, Xn naught, Xp naught. We don't know, they given Nd, fine, but we don't know the value of Na. Already we calculated one equation during the calculation of maximum electric field at the junction. That is Na into Xp naught equals to Nd into Xn naught. Okay, now just substitute the values of these three, then you get Na from this. Therefore Na is Xn naught by Xp naught into Nd into Nd. So now it is Xn naught 10 power minus 5 by, it is 10 power minus 4, 10 power minus 4 into Nd 10 power 17. So this is, by simplifying you get it 10 power 16 per centimeter. That's it. Now use this Na value. Already they given Nd. Substitute the values in this. Now, therefore V naught equals to, Vt into 26 milli they given, 26 into 10 power minus 3 into Ln of Na Nd 10 power 16 Na 10 power 17 Nd by Ni square 1.4 into 10 power 10 into 1.4 into 10 power 10. That's it. Just simplify this. This is 0.026 into Ln of see, it is 33 by 20. Okay, 10 power 13, 10 power 13 okay, so 10 power 13, 1.4 into 1.4, that is 1 by 1.4 divided by 1.4 is 0.51, 0.51. So it is 0.026 into Ln of 0.51 plus 13 into Ln of 10. That's it. So now it is, so Ln of this value is minus 0.67 minus 0.67 plus 13 into Ln of 2. Ln of 2 is 2.3. It is 13 into Ln of 10 is 2.3. So 13 into 2.3 minus 0.67. that is 29.23 into 0.026, that is 0.759, 0.759 volts. This is the voltage. V naught value is this much, 0.759. So you can take it approximately 0.76, 0.76 volts. See, my dear students, here just I substitute the values what we have. Whatever the values we have, I substitute that values in that one, not more than that. Okay. So next one is, so we have another problem, another topic in the another second part in this. The peak electric field in the device is, see this, in this they given a 0.15 0.15 megavolt per centimeter directed from P region to N region, 0.15 megavolt per centimeter directed from N region to P region, and 1.8 megavolt per centimeter. Okay, and 1.8 megavolt per centimeter directed from N region to P region. Okay, now see this. Now we know the equation for maximum electric field. The equation for maximum electric field is, so this is the second part. There is the equation for maximum electric field, that is minus NA into Q by epsilon into XP naught, or minus ND into Q by epsilon into Xn naught. Okay, just substitute the values. Minus NA we calculated 10 power 16 into Q 1.6 into 10 power minus 19 coulomb by epsilon 1 into 10 power minus 12 farad per centimeter into XP naught. I think so it is 10 power minus 4. They given XP naught 10 power minus 4. So 10 power minus 4. Now it is see 19. Now it is 10 power minus 3. Now this is 7. So now it is 10 power minus 5. Okay, by taking this one here, it is minus 1.6 into 10 power 5. Okay, now, or it is 0.16 into 10 power 6, or 0.16 mega volt per centimeter inverse. Now they given up negative. This is negative. The negative indicates, okay, the negative is indicates the slope is initially decreasing. So that is the meaning of this. Okay, maximum electric field is negative at junction. Already we got. So therefore, electric field is a E naught, magnitude of E naught is 0.16 megavolt per centimeter. Okay, and directed from, we know that, directed from N region to P region. N region to P region. To P region, that's it. So it is directed from N region to P region. That is the difference. Okay, now just go to the options. Now it is 0.16 we got, but here they given 0.15. Okay. Now 0.15 megavolt per centimeter inverse are directed from N region to P region. That's it. Okay. So that is the difference. So directed from N region to P region. Now option is, the correct option is here this one, and here it is the B. Both the cases option is B. Okay. So my dear students, just use the first collect the data what they given, based on that, okay, solve your problem. So next problem, we are moving to next one. See, the electric field profile in the depletion region of PN junction in the equilibrium is shown in below figure. Which one of the following statement is not true? So that means you need to identify the false statement, sir. False statement. See, this is the electric field profile on a PN junction diode, but they did not mention what is the N side and what is the P side. Okay. Now, first we know something about electric field. Now, just go first to write that electric field what you know. If we take a PN region like this, take a PN junction like this. This is P region and N region junction. Okay, we know the electric field profile here. Now, this is the electric field, distance x and junction. Let us take this is the depletion region. It filled by negative immobile ions on P side, positive immobile ions on N side. Okay, now here what happens is, so from this is the minus xp naught we mentioned, and this is xn naught, and this is 0 center. So this is minus xp naught, this is xn naught, and this is 0. Now our electric field profile is like this. It is constant. This is constant here to here, and next from here to here it is going to be increasing linearly. Sorry, slope is decreasing, negative slope, and here to here it is a positive slope, and it is constant 0. That means, so slope is negative. That is the important point. Slope is positive. Now see this, in P region slope is negative, in N region slope is positive. Now go back to your diagram what they given, just compare. In this plot is, this is the plot is increasing here, so increasing slope, here decreasing slope, negative slope, here positive slope. So once positive slope, this is the N region, so this is the N region, so it is N region, and from this we can write xp naught is 0.1 micrometer and xp naught is 0.1 micrometer. Fine. So it means a 10 power minus 5 centimeter. Next, this is N region. Sorry, N region is over. Now here slope is negative. So negative slope takes place in P region. So it became a P region. P region. And this is xp naught. So xp naught value is 1 micrometer. So it is 10 power minus 4 centimeter. So that is the data. Okay, and now we compare one by another. And one more thing, this is the electric field plot for uniformly doped junction. So P side is uniformly doped and N side is uniformly doped. Because of that we get the rho v value constant. See, now the left hand side of the junction is N type and right hand side is P type. So this is the left hand side, this is the left side, and this is the right side. So they mentioned, we got left side is R N region and right side is P region. Here also they given same. So this is the true statement. True statement. Both N and P type depletion regions are uniformly doped. So both are uniformly doped. Because of uniform doping only, our electric field is a linear one. So this is also a true statement. Next, the potential difference between across the depletion region is 700. Potential difference between across the depletion region is 700 millivolts. So that means this is the contact potential they given. V0 they given. To calculate the V0, we need NA, ND and NI. So the data is presently not available to us. Okay, just we keep it, hold it. Now we are going to next option. We check. If the p-type region has a doping of 10 power 15, they are using the condition if p-type doping is 10 power 15, that means doping on p-type is Na is 10 power 15 per centimeter cube. He is saying then the doping concentration in n-type region will be 10 power 16. Then Na is 10 power 16 per centimeter cube. Now we check this. See, already we know the value of xp naught and xn. Sorry, sir. This is xn naught. This is xn naught. Okay, now. So already we know the values of xp naught and xn naught. We have an equation Na into xp naught equals to Nd into xn naught. Okay, just substitute the data here. Now they given Na. If Na is this much, this is the, they are saying this is the Nd. Okay, now we check it. So from that I am writing the equation for Nd is xp naught by xn naught into Na. Just substitute the values. So xp naught value they given, we got 1 micro, so that is 10 power minus 4. 10 power minus 4 by xn naught. So xn naught 10 power minus 5. 10 power minus 5 into Na. So they are saying Na is 10 power 15. Now its value is 10 power 16 per centimeter cube. So that is the ending. So from this plot, if you take Na is 10 power 15, then we got Nd is 10 power 16. Also they given the same statement. That means this is also a true statement. So this is also a true statement. Now automatically the remaining is the false statement. You may not get this value. This is the option C. This is the false statement. False statement. Okay. So like that you can solve it. Now you observed or not, last problem and this problem both are depending on the electric field plot. Okay. Now, so we are moving to a next problem. See, consider a silicon PN junction at T equals to 300 Kelvin with the doping concentration of Na equals to 10 power 16 per centimeter cube and Nd equals to 10 power 15 per centimeter cube. The built-in potential barrier is VBI is 0.635 volts. This space charge width in micrometer is, they given epsilon r 11.7. Okay, free space permittivity 8.85 into 10 power minus 12 farad per meter. Okay, from this immediately you can write epsilon value simply 1 into 10 power minus 12 per centimeter, farad per centimeter. Fine. They given Na value and Nd value. So built-in potential means V0 they given. V0 they given. Okay. So 0.635 built-in potential volts. And Na 10 power 16 per centimeter cube. And Nd is 10 power 15 per centimeter cube. Yeah. So these are the NA and ND values. Then what is this depletion region width? They want in micrometers. Fine. Now I am getting everything is in centimeters. Now better to change those things here itself for meters. Okay, now epsilon value is 10 power minus 14. 1 centimeter, 10 power minus 2 distance, sorry, 10 power minus 10. 10 power minus 10 meters, farad per meter. Now NA is 10 power minus 6. Now it is a 10 power 10 per meter cube. Sorry, per meter cube. Now it is 10 power 9 per meter cube. Or you can use the same values. Finally, you change from that one from centimeter to meters. It's not an issue. Okay, now. So this is the equation for depletion region width. We know that. Open circuit condition this is because they did not specify it is under biasing. Now depletion region width W naught is 2 epsilon by Q into 1 by NA plus 1 by ND into V naught. We know that. Just substitute the values. Square root of 2 epsilon 10 power minus 12. Okay, no problem. You can take it in centimeters. It's not an issue. Into 1.6 into 10 power minus 19 coulombs into 1 by NA. NA value 10 power 16 plus 1 by ND 10 power 15 into built-in potential 0.635 volts. Okay, this now just simplify this. Square root of this is it became 10 power 7. 2 it is 0.8 times. Okay, now 10 power 7 by 0.8, 0.8 into, I am taking 1 by 10 power 15 common in this, 1 by 10 power 15, then it became 1 by 10 plus 1, so 1 plus 1 by 10 into 0.635, so it is 7, it is 10 power 8, it is 1.1, it became 1.1, so square root of 1.1 into 0.635 into 10 power minus 8 by 0.8. Now I am taking this one 10 power minus at outside, it became 10 power minus 4, 10 power minus 4 into square root of this data. So that is 1.1 into 0.635 divided by 0.8, that is 0.873, square root of it, it is 0.934, 0.934. Okay, this is in centimeters. Now you need to convert it. They want in micrometers, so this is 10 power minus 4, so it is a 0.934 into 10 power minus 4. We need in micrometers. Okay, so centimeter is 10 power minus 2 meters. You need micro, so micro by 1 micro by 10 power minus 6. Simple. Now it is, these two gets cancelled, so 0.934 micrometers, 0.934 micrometers. This is the depletion region width. This is the value of depletion region width. Okay, 0 point we got 934. So this is the approximate value. Okay, see here we use 11.8 and they given 11.7. That's why a little bit modification, slight change. Like this you can solve the problems on this. Now we move to next problem. See here, consider a silicon PN junction at T equals to 300 Kelvin, at T equals to 300 Kelvin with the doping concentrations Na equals to 10 power 16 and Nd equals to 10 power 15, built-in potential 0.635, depletion region width. Already we calculated just before this problem and now we got this value. Fine. Now the next extension of this problem is, in above problem determine the electric field intensity at the junction. That means maximum electric field they want. Okay, first of all we know that the maximum electric field is minus Na into Q by epsilon into xp naught, or minus Nd into Q by epsilon into xn naught. They given Na Nd, so you can take either this one or this one. Q we know and epsilon also we know. Now what about xp naught or xn naught? So once you know the depletion region width, from this you can calculate that. So that xp naught equation for that one is total depletion region into Nd by, already we derived all this, sir. Nd by Na plus Nd and xn naught equals to W naught into Na by Na plus Nd. This is the equations. Now I'm going to calculating this. W naught is 0.951. Okay, whatever the options they given exact value, I'm using that. 0.951 into Nd. So 10 power 15 by Na 10 power 16 plus Nd 10 power 15. So now it became, so its value is 0.951 into 10 power 15 by 10 power, take 10 power 15 common, then it became 10 plus 1 11, 11. Both will cancel. 0.951 by 11. It is 0.086. 0.086 micrometers. Okay, so one value is sufficient. Now based on this value, just to calculate the data whatever you want. We need maximum electric field at the junction. So the maximum electric field at the junction in terms of xp naught is minus Na into Q by epsilon into xp naught. So this is a minus Na they given 10 power 16. So Na, sorry, Na, okay, 10 power 16, fine. 10 power 16 into Q, 1.6 into 10 power minus 19 by epsilon. So we know the xp value in terms of micrometers. Okay, and just a minute, I am going to check the data given in volt per centimeters. So you can take everything in centimeters. So in centimeters it is 10 power minus 12 farad per centimeter, we know that. Now if you check the xp naught value, we got xp naught is 0.086 micrometers. Now it is 0.086 into 10 power minus 4 centimeters. So it is 0.0864 into 10 power minus 4 in centimeters. Centimeters. So now I am substituting the value of this. So it is 0. 864 into 10 power minus 4. Just simplify this, minus, so it is 10 power minus 3, so it is minus 7, and it is 10 power 5 minus 5. Okay, so 10 power 5 means it is we can write it as 160, and it is 864. Okay, now it is minus 160 into 864, so that is 138240, so that is 13.8 into 10 power 4, 13.8 into 10 power 4 volt per centimeter, minus of, we check the options, minus 1.38, in terms of 1.38 they given. Okay, so 1.34 into 10 power 4 they given, so 1.3, it's okay, minus 1.38 into 10 power, then it became 5 volt per centimeter. Okay, so just a minute, so 5 3 4 5 16, 10 power minus 3, 10 power minus 4 minus 7, then it is 10 power minus 5, 10 power 5 3 6, 160 into 864, 1.38 into 5, 1.5. Okay, correct option, this is the correct answer. Now, so there is a modification in these options, it is 5, it is 5, it is also 5. Okay, so that is the so need to check this, so there is a power 5 sir. Okay, that is a problem. Next one is a certain PN junction, with Ni equals to 10 power 12 per centimeter cube has a built-in potential of 0.56 volts. If the Fermi level on N side is located 0.35 electron volt above the intrinsic Fermi energy level, that means the given EFN is located above EFI at a distance of 0.35 electron volts. What is the acceptor concentration on P side? What is the acceptor concentration on P side? That is the option there. That is the answer they are asking. And they given contact potential to you, V0. V0 they given, that is a 0.56 volts. Okay. Okay. From this, you need to calculate the Na value. Okay. See, I am going to doing little bit workout on this. We know the equation for V0. It is Vt into ln of Na Nd by Ni square. Okay. By multiplying both sides with Q V0 equals to Q V0 became, this is 0.56 volts, then it became 0.56 electron volts is equals to Vt is, it is Q multiplied with Q, this one, and we know the equation for Vt, Kt by Q into ln of, I am writing this one is Na into Nd by Ni square, so Ni into Ni. Okay, now it became cancelled, Q became cancelled, so it is Kt into ln of Na by Ni into Nd by Ni. So now this is Q V0, which value is 0.56 electron volts. That means now I am writing simply this is 0.56 electron volts equals to Kt into ln of Na by Ni plus Kt into Ln of Nd by Ni. Nd by Ni. But we know this one. We know the value of, we know the equation, this one. This is nothing but a EFN minus EFI. Already we know the value of this. They given this one. Now just substitute. Now it is 0.56 electron volts equals to Kt into Ln of Na by Ni. Okay. Now, so they given Fn minus EFI. So 0.56 electron volts equals to 56 electron volts equals to Kt into Ln of Na by Ni, Na by Ni plus EFN minus EFI. Already they given EFN plus EFI value. That value is 0.35 electron volts. Just substitute that. This is 0.35 electron volts, and which is 0.56 electron volts. Kt into Ln of Na by Ni. Okay. Now take this one this side. From this we can write Kt into Ln of Na by Ni is 0.56 minus 0.35, that is 0.21 electron volts. Okay, now Ln of Na by Ni is 0.21 by Kt value at room temperature 0.025. 0.21 divided by 0.025. 8.4. 8.4. Okay, now Na equals to Ni. Take natural log exponential. Taking this ln into this side, then it became a e power Ni into e power 8.4. That's it. So Ni value they given, that is 10 power 12 per centimeter cube. So it is 10 power 12 into e power 8 power 4. E power 8 power 4. It is 4.47 into 10 power 3. 4.47 into 10 power 3. So therefore amount of acceptor doping or amount of doping on P side is Na equals to 4.47 into 10 power 15 per centimeter cube. 10 power 15 per centimeter cube. That is the value of Na. Just we check it. So 4.47, approximately 4.5. So approximately 4.5 or 4.6 to 10 power 15. Okay, so everything we taken clearly. Yeah, 4.47, 4.5 into 10 power 15. So 4.5 into 10 power 15 per centimeter cube. That is the amount of doping on N side, on P side. So that is a problem. Now see next problem. A silicon PN junction at thermal equilibrium is doped such that EFN minus EFI equal to 0.37 electron volt. in the N region, and EFI minus EFP equals to 0.3 electron volts in the P region. Determine the built-in potential in volts. Simple. 0.37 plus 0.33. So that is 0.7 over. Problem is all solved. Now simple. See this. Similar to previous problem. V naught is Vt into ln of Na Nd by Ni square. Nd by Ni square. Now I am multiplying both sides with Q. Q V naught. Okay. Otherwise, do one thing. We need to calculate V naught. So I am doing. Yeah. Now it is V naught equals to Vt is 1 by Q, Kt by Q, Kt into ln of Na by Ni plus ln of Nd by Ni. Now it is 1 by Q into Kt into ln of Na by Ni Na by Ni plus Kt into ln of Nd by Ni. So we know this. Therefore, V naught equals to 1 by Q into Kt into ln of Na by Ni is nothing but a EFI minus EFP plus it is nothing but a EFN minus EFI. This is the value. Now V naught equals to 1 by Q into, they given EFI minus EFP value to you. So EFI minus EFP 0.33, 0.37, 0.33 electron volt plus 0.37 electron volt. That is 1 by Q into 0.7 electron volts. 0.7 electron volts by Q, it is 0.7 volts. So that is the contact potential. Just whatever the contact potential equation we have, this one, it is converted in the form of energy band diagram. That's it. Okay. So 0.7 volts is the option. So we are moving to next problem. See, which of the following statements is true regarding PN junction? Homojunction. So the meaning of homojunction is both P-type material and N-type material both are designed by single type of semiconductor, silicon itself. If P-type material is designed by silicon semiconductor, if N-type is designed by germanium semiconductor, okay, they are called heterojunctions. Heterojunctions. Okay, homo means both N-type and P-type both are designed from a single type of semiconductor. So default PN junction is homo PN junction. Okay. Now see, which of the following statements is true regarding a PN junction? See, first option is they want true statement. True statement. The depletion region width decreases with applied forward bias voltage. So we know that when diode is applying forward bias, the depletion width is going to be decreasing, and in reverse bias, depletion width is going to be increasing. So this is the true statement. It is the true statement. Now we check remaining also. The depletion width is larger on the heavily doped side. No, the depletion width is increasing more towards less towards lightly doped region. Okay, already we discussed that. See, this is the PN junction. P region, N region. Let us take P plus and N. Now the depletion region on P side is this much. Now depletion width on N side is this much. That means depletion width is extending more towards lightly doped region. But the given statement is the depletion width is larger on heavily doped side. No, it is less on heavily doped side. This is false statement. Next, reverse saturation current depends on the applied reverse bias before breakdown. No, that is also false statement, because in reverse bias before breakdown, this is the plot. This is the plot. This is the breakdown. VBD. Before breakdown, it is not depending on the voltage. Okay, it is constant with respect to the applied reverse voltage. See, in this region, it is independent of applied reverse voltage. It depends on only minority charge which are available in that region at that time, or temperature. If you are increasing temperature, I naught is going to be increasing. For every 1 degree centigrade rise in temperature, I naught increased by 7%, and for every 10 degree centigrade rise in temperature, I naught increased by double. Okay, now, so this is also false statement. False statement. Next, the electron affinities of the P and N sides must be different. So what is electron affinity and everything we discuss later. Okay, when we are for that, you need to take a work function and different parameters you need to consider. Okay, later we discuss about that. So basically the electron affinities of electron affinity, okay, not depends on the type of material. That is the first point. That's why it is false statement. So this is the true statement. So we are going to next problem. In a PN junction, the minority diffusion coefficient 100 centimeter square per second on N side. Sir, listen carefully. Don't be hurry. See this. Minority diffusion coefficient. Okay, D. Minority. On N side. On N side, minority is whole. They given dP, which is 100 centimeter square per second. Fine. And 1 centimeter square per second on P side. That means dN is 1 centimeter square per second. Okay. Now, the ratio of minority diffusion lengths on N side to the P side is, take the carrier lifetimes on to be the same on both sides. We know they want diffusion lengths on both sides. Diffusion lengths on N side to P side. Diffusion length on N side to P side they want. We know the diffusion length on N side that is square root of dN into tau n by, on P side dP by tau p. But they given tau n equals to tau p. They given. So once tau n equals to tau p, then it became square root of dN into tau n by dP by tau p, and these two gets cancelled. Now square root of dN by dP. dN value they given it as 1 centimeter square per second, and dP they given 100. So 1 by root 100, it is 1 by 10. Okay, so that is 1 by 10, it is 0.1. That is the ratio of Ln by Lp. So it is 0.1 Ln by Lp. Diffusion length on N side by diffusion length on P side is diffusion length of electrons by diffusion length of holes is 0.1. Okay, is it okay, sir? Sorry, just a minute. This is the ratio. Wait a minute, sir. They asked one question. The ratio of the minority diffusion lengths on N side, sir, they want not this one, they want, so you can write 1 by ln by lp. They want this one. Sorry, sir. They want minority use. They use the term here minority. Okay, so just to go for 1 by, this is not that much. 1 by you have to be applied, not much. See, I'm sorry for that, sir. Here clearly they ask minority diffusion lengths on n side. On n side, minority charge carriers are holes. They want Lp by Ln. On p side is electrons, Ln. This is the data they want. Square root of for this dp by tau p and for this dn by tau n. But both are equal. Once both are equal, now it became dp by dn square root. Square root dp value they given it as 100. 100 they given dp value. 100 they given. Just substitute that 100 by 1 square root. Now it is 10. This is the option. Correct option. Not this. Sorry, sir. Okay, so just I concentrated on diffusion lengths, but they use the term minority here also. See, such type of mistakes we are doing in exam because point 1 also available there. Okay, don't do such type of mistakes. Okay, yeah. So this is the problem. Next we are moving to next one. See, let J1 be the total current density through a germanium PN junction when connected in forward bias to an external voltage V. So external forward voltage is V. This is a germanium diode. Okay, its current density is J1. Fine. For this, the band gap of germanium is increased. So let us, the energy band gap is Eg. Let us assume the band gap of germanium is increased. Band gap increased, sir. Let us take Eg1. Now there is a second one, Eg2. Via band gap engineering without changing Ni, and a new germanium PN junction is fabricated and connected to the same external voltage. Okay, same external voltage V in the forward bias. Then the new current density is J2. And here sir, they are saying energy gap second case is energy greater than energy gap in first case. Okay, then you need to compare these two. One thing, sir, energy gap less in this sense. Okay, once energy gap is less, just in this case, first case, this is, let us take case 1 and this is case 2. In first case, let us take, this is the energy gap Eg. This is the energy gap. Second case, this is the energy gap. They increased the energy gap by using some mechanism. Whatever the mechanism they use, and we don't want here. This is the energy gap. Okay. Because of, so same voltage they applied both the cases. Because of this voltage, due to less amount of energy gap, if you are going to get 100 carriers, 100 covalent bonds if you are breaking, and here due to high energy gap you can break only 70 covalent bonds. Once 100 covalent bonds you are breaking means 100 electrons, 100 holes you get minimum. Okay, 100 plus 100, 200 charge carriers you get, but here only 140 charge carriers. Now here current density due to 200 charge carriers is J1. Here current density due to 140 charge carriers is J2. Now J1 is greater than J2. Because of low energy gap with the same voltage, first one gives the high current density. This is the option. Okay. Anyway, okay, thank you students. Thanks for spending your valuable time with us. Now after that, within half an hour we have another session. So we continue the problems in that session. I'm thanking one and all for spending your valuable time with me. Okay, so valuable time with us, and don't forget to use my code during subscription VROW10, and please click on the bell icon for getting the notifications. Okay, and please join our Telegram group to get the latest updates on our upcoming videos. And please subscribe, don't forget it. And give your valuable comments on the YouTube to strengthen ourselves and to provide a better and quality information to upcoming students. And that comments is the boost to us. Okay, now thank you, thanks to one and all for spending your valuable time with us. Once again, I am welcoming you all to India's largest online learning platform, Unacademy. Thank you very much.